So I'm really excited to be here today to talk a little bit about Microsoft's journey with Git. For those of you who think that moving Windows onto Git was kind of the ending of the story, it really isn't. That was just the beginning. So I want to share today some of the challenges we faced along the way. Talk a little bit about the perf and scale work that we've done inside of core Git and inside of VFS for Git. And finally, I'll touch a little bit on kind of where we're headed next at Microsoft. So just a little bit about me. My name is John. I've been with Microsoft for about 6 years after a decade in kind of the gaming middleware. 4 years ago, I changed roles from an engineer back to an engineering manager. So I write much less code than I did as an engineer. But I moved on to a team that I'm really passionate about, the Git team, the team responsible for really helping Microsoft onboard onto Git. So our team is responsible for building Git for Windows, building the Git credential manager for Windows, building VFS for Git. And I should pause. Most of you will know that as GVFS. We renamed it to VFS for Git. Also, if I say VSTS, I'm sorry. That's a very ingrained habit. It's Azure DevOps now. I'm working on it. We also contribute to core Git. But one of my team's primary responsibilities is making sure these big Git mono repos inside of Microsoft are successful. And the biggest among them is Windows. So in early 2017, we moved Windows onto Git. And the technology we used to do that was VFS for Git. And what VFS for Git allowed us to do is really kind of eliminate the working directory as a scale vector in Git, which was one of the big blockers. If you remember, Saeed in 2017 talked a little bit about 5-minute status times inside of the repository. But being on top of VFS for Git really eliminated that. But Git is not just a big repository in terms of the working directory. I mean, it is. But it's also a repository whose history is growing very, very fast. Automation was creating a good amount of that commit history. This is the Windows repository as of January. It has 3.1 million commits and 24 million, almost 25 million trees. And you see kind of where VFS for Git takes over. There's just one branch visible to the client. And in a clone where you haven't started working yet, there are no objects present. But the presence of so much commit history and so many trees was really a scale vector that we hadn't planned for in the initial implementation. Because we made the decision early on in VFS for Git that we weren't going to try to virtualize commits and trees. We assumed they were small enough. We assumed that, well, we didn't assume. We measured that when we missed on a commit or tree and had to go back to the network to grab it, it resulted in a really, really bad experience for the users. And so we made the decision that we would keep all the commits and trees for the repository locally so that users didn't have to suffer those tree misses. Here's how the repository has grown since its inception. And you can see that it has been just steadily accelerating for the better part of all of 2017 and the first half of 2018. And as it did, the repository performance degraded. And that was one of the big things that we had to go fix. We had moved on to the technology. We had moved Windows onto Git, but we hadn't yet finished that cultural change of being on Git. It means different things. Windows was coming from a world, a centralized world, where tools could interact with a centralized server frequently, and it was almost no impact on anyone's world. But when these same tools were brought over to Git, which is a totally safe thing to do, right? Let's not boil the ocean as we move the repository. But as these tools were brought over, the behaviors of the tools didn't change. And so the tools were interacting with the repository and continuing to create just a ton of objects. So let's take a look at just 1 week in early 2018. This week, there were 92,000 commits created in the repository. And this is not a special week. This is one picked literally at random. Of those commits, 31,000 were build machines doing build machine things, checking in little version changes across the repository. Another 25,000 were various pieces of automation that were running through the PR APIs, creating more commits. 21,000 were what I would call developers at their workstations doing their jobs. Those are the important ones. Those are the ones that we really want to enable people to be successful with. And another 15,000 were code movement up and down the tree. Windows is organized into a hierarchical series of branches so that code flows up, code flows down. And we needed to create about 15,000 commits just to flow the code in any given week. So all of this commit, all these commits were being introduced, and 77% of them were not developers doing their work. And this started to contribute to the repository was growing out of control to the extent where we needed to mitigate the impact of that graph size on repository performance. And so we built the serialized commit graph. Now, what the serialized commit graph is it is an efficient, compact storage for commit metadata. The parents of a commit, the generation number of the commit. And Stoli talked last year at Git Merge about how much of a difference it makes in the time we spend parsing commits. So if you're interested there, I'd encourage you to watch his talk from 2018. But this last year, we taught the commit graph a new trick, and it is storing generation numbers. What that lets us do with the commit graph is answer questions about the topology, things like git log one line. So prior to the commit graph, so if we disable it entirely, a log one line inside the OS repository will return in about 40 seconds, which is not a good experience for anyone. And this is actually the best run I got. The first one took 90 seconds as it warmed up the disk cache. With the commit graph, we're now returning those results in under a third of a second. So this is a huge change, a huge positive benefit for the developers working inside the repository. Now, of course, you can say, well, sure, but the Windows is a almost pathological case. Does this help other repositories? And sure enough, it does. In terms of the Linux repository, without using the commit graph, we get the same log one line performance of about 8 seconds. And when we enable the commit graph, it'll return history in under 1/10 of a second. So this is something we're really excited to be able to do inside of core Git and share with the community. This is available in Git 2.20, and I'd encourage you to try it out on your own repositories. It's not on by default yet, so you can go in with git config core.commitgraph true, and git config gc.write-commitgraph. That will automatically write the commit graph during GC. And if you want to go ahead and start getting the benefits, just call git commit graph write. And so I encourage you to try it out. Let us know how it works for you. And I'm just happy to have that available for everyone. So we got to a good spot with the commit graph, but don't forget that these automation were generating trees at a rate of almost 8 to 1. For every commit, we were generating 8 more trees. And we were starting to find that even the object lookup was showing up in the hot path. And that was, we took inspiration here from the Azure Repos server to bring the multi-pack index to the client. And so what the multi-pack index is kind of the not-so-secret sauce of Azure Repos that helps it scale up to these large repositories. The service needs to index a lot of packs efficiently. And VFS for Git has a similar design. As these pack files are created to deliver the commits and trees from our cache servers to Windows developers' machines, they are accumulating pack files. And as the pack files were being accumulated, we were finding we were just taking more time inside object lookup. Well, what multi-pack index does is really accelerate the time it takes to find a particular object. So it's worthwhile to review kind of how packs and pack indexes work in Git. A pack index is, I'm simplifying a bit here, but it's a map from an object ID to the offset inside of the pack file where you can find the object. Each pack has a corresponding pack index. So as you increase the number of packs, there's a corresponding number of pack indexes that you have to troll through to find the object you're looking for. In a normal repository, there'll be a handful of these, and it's not such a big deal. You'll find these by just going through and probing. All right, do you have my object? What about you? And it'll be a binary search, which is reasonably quick. What about you? OK, once I find it, then I know I can stop looking. It has a nice property of being able to early out. But even being able to early out, we were averaging these times just creeping up to a place where it wasn't feeling great anymore. So we went and put the multi-pack index in front of them. The multi-pack index is very similar to a pack index, but it's got one additional field. Which pack file can I find this in? It also encodes, of course, the offset and the object ID. The object lookup proceeds in the exact same manner as it does in the pack index. A binary search through the multi-pack index will point to a row. The row tells us both the pack and the offset. So that lets us efficiently index hundreds, 500, up to 1,000 packs in a developer's working environment, which really kind of helps perf. But aggregating all the pack indexes actually helped in one other way. Prior to multi-pack index, we had to actually go and disable abbreviations in the repo, because searching the pack files to find the proper abbreviation length took too long. So just to review how that works, when we're going to compute the abbreviation, we'll scan through each pack, trying to find the object, as well as the two bounding objects. And we need to do that so we know, well, how far do I have to go down that SHA to get a unique string? This has the property that you cannot early out. A conflicting object may be well past the pack that actually contains the object. So we need to consider each pack in the packs directory. Multi-pack index helps considerably here, because it's just one pack file to look through, and we're able to find exactly where the object is, and we look on either side, above and below, to find whether or not we can abbreviate how far to go to get that unique abbreviation. So it's also something that we hope is applicable, the MIDIX, that is, the multi-pack index, we hope is unique or is available for usage on Git hosting services, because this is one of the pieces that helps Azure Repos scale so well. This is also available in Git 2.20. You can turn on git config core.multipack index to true, and then you can write it with core or git multi-pack index write. This is one where we're really looking for some feedback from the community on this. If this is something you're interested in, how do you see yourselves using it so that we can kind of efficiently plan where we go spend some more time building this? We have a few things that we know we want to do in terms of incremental writes and a few other features to make it more robust and quicker to deal with. But I do look forward to hearing from the community if this is something that you guys are passionate about as well. So now let's change topics a bit and look at the impact of the growth of the repository on network operations. As the repo grew, we found that the perf of network options was declining as a function of the graph size. And you can see here, this is the times to fetch in the OS repository. The red line is the median, so 1 in 2 fetches took that long. The orange line is the 80th percentile, so 1 in 5 fetches took that long. By June 2018, fetch had crept up to 350 seconds, 5 minutes, in the OS repository, or the P80. 1 in 5 was 5 minutes long. That's time to go get coffee and come back and still be frustrated that it hasn't finished. Terrible, terrible user experience. Automation, the automation that we talked about earlier, was adding enough commits and trees that these daily pack files that the cache server were producing were averaging between 150 and 250 megabytes each. And so we needed to attack this problem from multiple angles to be able to actually get back to a good experience in the Windows repository. The first was engaging with our partners in the Windows development group. So Windows did an excellent job once we kind of went to them and said, hey, we think there's a problem, and we need your help to fix this. The Windows group did a great job going through and auditing all of their automation, figuring out ways to reduce the number of commits that were being created in the repository. In July, when we really started the effort, we were creating 200,000 commits in the repo. But by January, we were creating just over 50,000. These are commits we attribute to automation in some form or fashion. And it's still going down, unfortunately. So this helped immensely mitigate the perf, the degradation that the graph size was causing. But while we were doing this investigation, we noticed there was a cohort of users for whom fetch perf was still great. In fact, it was so good, they were overwhelming our statistics. And we didn't notice this because we were measuring wrong, which is probably a story for a different conference. But we knew that if we could emulate what they did, we could better serve other users. So remember, we had regressed up to 350 seconds in June. And what we did is we emulated these users who had good performance. Because VFS for Git has a long-running mount process in the repository, we could offload that prefetching of commits and trees to the background, let the machine pull those down while the user is not using their machine, so that when they do need to run fetch to update the local refs, they're already more or less up to date with the big downloads that would have to come down. And the only work they need to do is receive new refs from the service. This now means most fetches were no ops and brought down the P80 and the P50 to just under 15 seconds, if I remember correctly. So that's been a huge positive impact in those developers' lives. And we had also hoped that prefetching in the background would speed up push, which had regressed similarly too. With the assumption that, well, push needs to walk commits to discover what needs to be pushed. If developers aren't staying up to date, we could explain the regression in push by having to fault in these commits and trees as we do the walk to build the pack file. And we had hoped that shipping prefetch in the background would really help push as well. It didn't at all, because we didn't measure first. And this is one of the critical things that we need to do as devs building software, especially tuning for performance. Don't guess. I'm guilty of it, clearly. But what we had been doing while we were investing in Fetch, while we were investing in Middix, we had also been building out the Trace2 API in Git. What Trace2 lets us do is put timing blocks around very specific areas in the code. It allows us to get much finer grained detail in our measurements. So when we initially rolled out to Windows, the granular measurements we had on developers' command perf was essentially a pre-command hook that says, hey, status is about to run, here's its command line, and then a post-command hook. I'm all done, I succeeded. It took 2.5 seconds, which is good for reporting on the aggregate, saying, yeah, its status is generally OK, but it's not good for digging in deep to figure out where a population is spending its time. So the push investigation was actually a perfect opportunity to go eat our own dog food here. So we went through and we instrumented several blocks inside of the push and then rolled that out to the Windows developers so we could find out where they're spending time. Now, interestingly, it wasn't exactly where we thought it was. So why was it slow? So look through the things that happen at push. First, we go get the current refs from the service. We prepare a pack to send. There's 3 stages there. We need to enumerate the objects. We need to compress the objects and write the pack file. And then we can go send the pack to the service. And it's easy to look at those and squint and say, well, I bet compression's taking a long time. Or, hey, if the network's involved, all bets are off. When we started getting Trace2 data, we were surprised. Because the users, by the percentage of time they spent enumerating objects, we can see that the vast majority of our users were spending 60, 70, 80% of the time during a push just walking the objects to figure out what they needed to include in the pack file. VFS for Git had brought a good implementation of a lazily sparse work tree to Git. Now what we wanted to do is bring that same sparseness to push. To build a foundation to talk about these changes, let's kind of review how push works today. The first thing that push needs to do as it's doing its job is walk from the remote refs and the refs that you're trying to push to figure out which ones need to be included. Anything that's available on the remote is uninteresting, but anything that you're trying to push that the remote has never seen before is interesting. And so Git will keep walking, trying to find the set of commits that are novel to the server. Those are the interesting commits. And those uninteresting commits that are direct parents of the interesting commits, and the interesting commits kind of make up the frontier of the commits that need to be under consideration when Git goes to build that pack file to send up. Once Git has established the frontier, the next thing it does is go through commit by commit, walking down the trees to the objects, marking them as uninteresting, if they originate from uninteresting commit. And it does the same thing for each uninteresting commit. And then when it does that object walk for interesting commits, it will mark those new trees and blobs that are novel to the server as interesting. And that will progress all the way through until we've fully enumerated the set of objects that are new to the server. This is a completely sane way to do it in a repository of not unusual size. But what we were seeing in the Windows repository is to find 100 interesting objects, we were walking 3 million uninteresting. What we want to do with the sparse object walk is take a leaf out of how VFS for Git works. It works on the assumption that most developers don't touch most of the tree in a repository as big as Windows, especially not in the usual case. In fact, most developers only work in a very small subset of the tree, what they're specialized in. And our motivation was try to bring that modified behavior to the push object enumeration. The new algorithm tries to early out from descending through the objects as quickly as it can, and it does that by moving the walk into path space. So we go to the root trees for each commit in the frontier, and then we move into a directory-based approach. We bring the path into the equation. So this tree on this commit references 3 paths, A, B, and C. All of those happen to be uninteresting because they're referenced from an uninteresting commit. And we walk all the trees at a particular layer in the hierarchy, deciding whether or not the tree is interesting or uninteresting. When we find a path who only contains uninteresting trees, we can eliminate that entire path from further walks and really cut down on the amount of data that we need to process. When we have paths like B that contain both interesting and uninteresting trees, we need to deepen there to find out, well, what else do we need to learn? So we pick up those trees and continue processing them on a path-by-path basis. We'll build a hash map that contains each OID and whether or not those objects are interesting or not. So here, B contains 2 subdirectories, X and Y. And this particular one has an uninteresting X, but when we move to the uninteresting Y. But when we move to the interesting one, that has the same uninteresting X, but an interesting Y and a completely new Z. Because we're in path space, we know at this point we can eliminate X and Z from consideration. X will be entirely uninteresting, and Z and all of its descendants will be entirely interesting. So this allows us to really optimize how many objects we look at. We move from parsing on a very simple push, a small topic branch, from enumerating 400,000 objects, trees, to just 37. It dropped the pack objects time from 10 seconds to under 4. And it dropped the overall push time from 15 seconds all the way down to 8.5. And remember, this is for a relatively small topic branch, so I'm really excited to see this roll out to Windows developers. And it's also currently under review up on the mailing list. So if you have opinions on this, we do look forward to hearing them. So we're really hopeful that once we roll this out, we'll have that same sustained improvement in time, in push time, that we did in Fetch. So I want to move on real quick and touch briefly on another piece of work we did to really bring the Windows repository performance in line with their developers' expectations. And that's to do with status. Remember, Windows developers are moving from a centralized system, a system that can very quickly answer, what's dirty? What do I need to care about? And moving onto a system, even like VFS for Git, they had seen their status times go from half a second, 750 milliseconds, up to 2.5, 3.5, 4.5 seconds. And there was general dissatisfaction with that performance. And so we took a little bit of a cue from how IDEs handle this. Because we have the virtual file system layer that sits right above NTFS, we can monitor for writes onto the repository. the projected file system can talk back to the mount process and say, hey, I see this editor just wrote this file. You may want to do something about it, which it's happy to do. The VFS for Git mount process will then go responsively run status and serialize the result to a cached file. This means that once that result is available, when a user queries for status, VFS for Git, or actually Git, this is all built inside of Git, is able to see there's a cached file and immediately respond with those results. This helped us move the status perf of the Windows repository, which was sitting around 3 seconds at the median, all the way down to about 750 milliseconds, bringing it kind of more in line with the expectations of the developers, and really just kind of removing those paper cuts that were introduced from the transition from the centralized system to Git. So what's next for Microsoft, and what's next for VFS for Git? It's Office. And the challenge with Office is a completely cross-platform team. Office ships on Mac, Office ships on Windows, Office ships on iOS. Office ships nearly everywhere. And that means that the development teams can't just work on Windows. And so one of the big things we're doing now is bringing VFS for Git to the Mac. And our friends over at GitHub are bringing VFS for Git onto Linux as well. But for the Mac work specifically, we are porting so that we can host Office. And that means that we can't rely on ProjFS that we can rely on Windows. And Mac doesn't have an equivalent that we found performed as well. So we're writing a text for Mac that simulates the behavior of VFS for ProjFS, but on Mac OS. And in doing that, what we hope to provide is a very responsive feeling system, one that works as well as VFS for Git does on Windows, but for the Mac platform. We're doing that by porting the user mode pieces of GVFS to .NET Core. So those will be able to run anywhere. Introducing a little platform abstraction layer to make sure that where we need to call into different platform-specific APIs, it's all running through one place, and then swapping out ProjFS on Windows or ProjKext on the Mac. And so we're really looking forward to bringing what I think will be the second largest repository in the world onto VFS for Git. And I just want to say thanks to the Git community, contributors and maintainers for being just very welcoming. And we can't do this without all the work that the community had done to get to this place. And I'm just really excited to be a part of continuing to make Git the version control system of choice. Thank you.